So let's talk about some of these questions out of the book. That question 16, because that's kind of a big idea that they tend to have these type of problems just piece on the test. So here's the story. So if you look at this diagram, so when in doubt, draw a picture. So here's the stick, boom. Here's one kid, boom. There's the other kid. So this is what I tried to show you all yesterday when we had the weight that was suspended between the scales, and depending upon where you put that load, that altered the reading on the scale, but ultimately everything had to add up to equal to 0. So they've got a 1.8 meter long rod, and then they're hanging, the older child supports twice as much weight as the younger child. How far is the bucket from the older child? Okay, so let's say this is going to be the older one, right? And so just begin to think this through. If the older one is going to support twice the weight, where are you going to put the bucket? Closer to the older one or closer to the younger one?
Closer to the older one.
Closer to the older one. Okay, so right away you know that that distance to the older one has to be bigger than, that distance has to be smaller because they want to carry more of the weight. So basically this is a torque problem, okay? So imagine where that thing can pivot and you've got this action going. So you want one person carrying twice the force, so we're going to let that distance be x. Okay? I don't know what it is. I'm just going to call that x, because that's going to be the distance to the to where that bucket is. Now, what's left is this person carrying a certain amount of force, but if the total length is 1.8, what's left over in this gap?
Board.
No.
I don't,
If this distance is x to the bucket,
oh, x minus 1.8. Or 1.8 minus x, sorry.
1.8 minus x, right? True. Good? Then it's just an algebra problem. So because of the fact that you just want this in terms of force, okay, you really don't actually know the numbers, so you can get this as, you can distribute that, do a little bit of rearranging, there you go. Okay, now, 18 is a similar type idea. So you've got two scales, and you got this action, you got this action, and then here's this person stretched out in between. So on this one, you're told that it doesn't make, they just happen to be working in pounds. It says, what is the student's weight? So here's the story. So you got 100 and you have 65, right? So if you look at this in terms of what's going to happen, so you've got, and what you're trying to figure out basically on this one is that where's that center of mass? So what you can do is the same type idea. So you've got 65 and you have 100 and what's that total length, like 2 meters? So the easiest way to do this one is say, okay, hey, I'm going to let this pivot around a point. Okay? So if that's the case, then, because what you're trying to find out, what is the student's weight? And her feet are directly over one scale, her body is positioned, here you go. So if you let this, and what I did is I said, okay, hey, I'm going to let one distance be like 2 meters. Okay? Because of the fact that it's right out there on the edge, and that's that 2 meter distance. So if you look at this, this torque is going to be like 65 pounds times 2 meters. Because way out here on this edge, that's 2 meters away, that has a reading of 65 pounds. So that's generating that amount of torque. So if everything's going to be the same, then you've got to have the total, which is 165, times x. So these two things have to be equal. So if you take 165 times x and 65 times 2 meters, then you can figure out what that missing value is. So on 18, when you're trying to figure out, what are they trying to figure out?
Student's weight.
Yeah, the total student's weight. So, or you can just really make it simple and just add the two values together. Doesn't make any difference. Okay, now, probably the most complicated one is the problems 1 and 3. So, on those, here's what you want to look at. So, you got this scale, and then you got this other scale, and the person standing here, wish I could draw better, and that's 1.5 meters, like this, and the total length is 2 meters. So you have two different, like, basically equilibriums taking place. So, bless you. I called this like certain amount of force on 1, certain amount of force on 2, and then you got gravity pulling down. So if you think about it, this force here has to be balancing out a downward force. So this one has to be providing an upward force. This one has to be providing an upward force. And you've got the one in the middle that's being pulled down because of gravity. So when you add all of those together, what does it have to add up to? 0. So if you go, okay, force 1 plus force 2, and you're told that you got a 64 kilogram person. So how can you find the weight of the downward force of a 64 kilogram person?
Times 9.8.
Yeah. So if you do that number, I think it's like 600 and some. And obviously one of those has to be negative value. I made that the negative value, right? I think it's what, 627? All of that's going to add up to 0. Okay, so that's one set. Now here's the problem. You have two unknown variables, so you got to figure out something else. So this is where now it kind of turns into a torque problem. So this person sits, what is it, 1.5 meters?
Yeah.
So if you take that negative 627 newtons times that distance of 2 meters, so that's how much torque is being created trying to make this one go in that direction, okay? Well, that other one has to generate a torque to balance that out. Otherwise, it's going to spin in that direction. So the other one then is going to be that second force that you don't know times 2 meters, and those two values have to add up to equal to 0. So this allows you to find that second force. Because you can't get this, you don't know force 1 or force 2 here. But this one, you can solve for force 2, and then once you get force 2 out of here, then you can put that back up into here, and then you can find that force 1. So, and pay attention to this one. It says, what is the reading on each of the scales? So on problem number 1, you should have two answers. The scale on the right and the scale on the left, okay? So in newtons, the scale on the right, this is a big gap shine, okay? The right scale should be between 400 and 500 newtons, and the left scale should be around 150. Okay?
I'm good with that.
Now, 3 is probably the toughest one conceptually. So here's this table, right? And you've got Billy, Joe, Jim, Bob out there on the edge, right? And this is 0.55 meters. So, and the total length is 2.1. Okay? So this is what I tried to show you yesterday with like the board. okay, when you're trying to balance this thing out. So you have two torques about this edge right here. You've got the guy out there on the edge, which is trying to make that table go in like a clockwise direction. You've got the center mass of the table, which is creating a counterclockwise torque. So when at some point, those are exactly going to balance out. Now, if he goes to anything past that equilibrium point, the table's going to rotate, he's going to fall. So you just set those two torques equal to each other. So that's the whole point of this. You're going to set up two different torques. So what's the guy's mass, like 56? What's his mass?
Yeah, 56 kilograms.
And the table is 70?
Oh, no, the table is 56.
The table is
dude
56.
70.
The table is 56 kilograms. He has a mass of... So, relative to where this thing is going to spin, this is going to be the center mass of the table. So you're going to take 56 times G times the distance to get to the center mass of the table. Then that's going to equal 70 kilograms. Do they actually give you that distance, or is that what you're trying to find? You got to figure out how far out he can walk.
Yeah.
So you got 56 times G, and that distance is, for the table, 0.50 meters. And then you've got 70 kilograms times G times whatever that distance is. Now, where this gets a little bit tricky is because on that one, it's weird how they ask that. It says, how close to the right edge of the table can the guy stand? So it doesn't, what you're going to find is the distance from this table leg right here, but it asks for how far away from the edge he can stand. So you just have to figure out that. So that answer in meters should be between 0 and 0.2. Cool with those? Okay. On the multiple choice. So let me there's certain ones I want to go through on this. Let's start with number 1. So anytime you have measurements, and I probably should stress it more than I do, but it's kind of a minutia thing, and I want you to see the big picture. But in reality, once you measure something, there's always a certain amount of uncertainty in that measure. So what they're saying on problem number 1 is that you're moving at 3 meters per second with an uncertainty of plus or minus 0.2 meters per second. So in other words, that velocity could be somewhere between 3.2 meters per second all the way down to 2.8 meters per second. Okay? Somewhere in that gap. We don't know exactly what it is. We're pretty confident, hey, it's somewhere in this gap. We're going to call it 3, but in reality it might be 3.2, it might be 2.8, because there's some uncertainty in that measurement. Now, so what's going to happen here? Got a frictionless track, collides, sticks. So it's a California problem, right? Because they're going to move off together. So because they're going to move off together and the masses are identical, if it was moving at 3 meters per second and you double the mass, what should become the new velocity then?
1.5 meters per second.
1.5, right? Because of the fact that you're told on this one that if it was exactly 3, that would be moving at 1.5 meters per second. So if you knew it was exactly 3 meters per second, it would be cut in half. Now we're going to do that same thing here. If it was 3.2 meters per second, let's say it's on the high end, if it was at 3.2 meters per second, what would that velocity be? Oh, that's going to be half of that. That would be 1.6. 2.8 would be 1.4. Okay? So basically you look at the extremes and go, okay, hey, if we double the mass, if that was the actual velocity, this is what the new velocities are going to be.
I was
When you get to question number 2 about the train, a couple of things about train questions. The two most important words on problem number 2 are constant speed, okay? So this is not an accelerated, what we call frame of reference. So the train's just moving along at a constant speed. It's not speeding up, it's not slowing down, you don't have to worry about that. So the spheres are moving directly towards each other. So in other words, what that's saying is that if you were inside the train, okay, and Einstein was famous for train experiments. If you were inside the train, you would see these two objects moving towards you. Okay? You're inside the train. You can't now. If it's at a constant velocity, you can't even tell that the train is moving. Maybe you hear the clickety-clack, but from a physics perspective, you're moving, and you're moving with the train. So, with this one, it says, what's the velocity, the center of the mass, frame of reference of the train of a person standing at rest alongside the train? So imagine this. Here's Cohen, and he's seeing Will go by in the train, okay? Constant speed. So, a couple of things are about this. When it asks for what's the velocity, the center of mass of the spheres within the train, because they're both moving, same speed, within the perspective of the train, the center of mass is still going to be the same center of mass, and that's going to be at 0, because of the fact that if you're within the train and you're seeing these two objects move, that's what you've got. But if you're Cohen on the outside looking in, you're going to see the train and everything else going, in this case, to the east? Mm-hmm. Yeah. So Cohen on the outside is going to see the center of mass move to the east. So Will, inside the train, he can't tell any difference. Cohen is going to see the whole center of mass move to the east. When you get to multiple choice question number 3, okay, the answer is not D. I know you want it to be because that would be the simplest. Now, here's the story. When you lower that down, are you changing the energy of the spring?
Yes.
Yes. And you know us equals 1/2 kx squared, right? Mm-hmm. So you can figure out how much the energy of the spring is increasing. You just do 1/2 kx squared, right? Now, when you lower it down from a gravitational potential energy, what's happening to the amount of UG? It's decreasing, right? And that's just going to be mgh. So the overall net change is going to be the difference between how much UG you lose and how much us you store.
Would it make sense to be, would it make sense to lose energy?
Huh?
Would it make sense to lose energy on that?
It could, very much so. Because if you look at what the decrease in the UG is versus the increase in the us, you're losing more UG than you're gaining in us.
Is gravity more efficient than the...
No. It's just how far it got compressed. It's just a function of that. It isn't a function of efficiency. Okay? Now, when you get to question number 4, so here's the rule when you're dealing with center of mass. Unless there's an outside force, center of mass remains stationary. Mother Nature's a lazy prima donna. So what you have here is you have this person standing out here, and they're going to walk in this direction. So you kind of have to answer this question, they've got a scale underneath and they've got some marks. So you kind of need to get an idea of when they start, where's that center of mass? Well, if the person's out here and the raft that they're walking on is here, Obviously, the center of mass of the raft is right here. The person's out here. So right now, where's the center of mass before the person starts to walk? About here. Okay? So here's the center of mass, right here. So what that means is, barring any external forces, the center of mass is going to remain at this point. Okay? So when that person walks this way, what does the raft have to do?
Move backwards.
It has to move backwards so that the center of mass remains at the same location. Okay? So the person walks one way, the raft is going to go in the other to keep the center of mass at that same point. So you kind of have to like count the marks and see where those marks are. So now when you get to 5, 5's a good question. I like number 5. So let me kind of give you this visual. So you've got a rod, it can spin about this point. So things are going to come in, it's going to head it, it's going to have a certain amount of initial momentum, and then afterwards that's going to spin around and some amount of final momentum. So let's just put in some numbers. So when I take a problem like this, I'm more of a numbers kind of person. So I just randomly said, I'm going to let that have a momentum of 10 Newton seconds. It could be 20, I just happen to pick 10. But here's the bigger idea. If the initial momentum is 10 Newton seconds, okay, and it says the sphere rebounds along its original line of motion with magnitude of PF. What is the magnitude of the angular momentum of the rod immediately after the collision? So if this comes in at 10, when it bounces back, what would be the sign of that momentum?
Negative.
Negative 10. So that's going to be like, I'm just going to make the math easy, and I'm going to say, hey, that's going to be negative 10 Newton seconds. So if I take, am I changing momentum? Momentum final minus momentum initial, which is going to be negative 10 minus 10. So what's my change in my momentum going to be? 20, which is basically, in effect, in terms of magnitude, it's like I'm adding the momentums together. Okay? Because of the fact that I'm going to have a change in direction. Okay? And that's what is important, is that you realize, wow, this thing is going to bounce and there's going to be an overall change in the direction of this thing. So right away, knowing that idea right there, this is a multiple choice. What two choices can I eliminate at this point?
A and C.
I can eliminate A and C, okay? Because it's going to change direction. I can conceptually get rid of A and C. Because I'm basically going to add this stuff. Now, this is where momentum meets angular momentum. Angular momentum equals I omega. True? Cool with this. Now, here's where this gets a little bit wonky, but not bad. You also know V equals R omega. True? Mm-hmm. So if I solve this for V, or solve this for omega, I get V over R. And there's a method to my madness, and you'll see why this is going to play out large. So this is going to be I times
V over R.
V over R, right?
Mm-hmm.
Now, here's the story. What's the simplest way to calculate moment of inertia?
What have?
No. The simplest way, the most generic way to calculate moment of inertia.
R squared.
mR squared times V over R, right? True?
One of the R's cancels, right?
Yeah, and you get
MRV.
MRV. Not Mr. T, but Mr. V. Okay? So you have MRV. So now, knowing that, okay, I'm going to rearrange this just a little bit, and put that MV times R. So what do you get when you multiply
M
M
and
and
V.
R?
M and R or
See,
M and V?
mass and velocity.
Momentum.
Momentum. So L equals
PR.
PR.
Personal record.
There you go.
Yay.
There you go. Okay. So hopefully that
Okay.
gives you some hints on what you can do on 5. In terms of my questions, I wish I was clever and I had this plan, but it just randomly worked out that way. On the questions, on the what I typed up, on question number 4, every answer should start with a 4.
Wait, look.
Number 4.
Yep.
Huh?
That's what I got.
Yep.
On question 4, every answer should start with a 4.
You got unforeseen,
4,800.
Okay? Preston, do you not like that?
No.
Just telling you. Okay? Every answer should start with a 4. Your answer to number 2, about forcing the rockets, that should be something times 10 to the 7th. Your answer to number 3, again, I wish I was clever, but your answer to number 3 should be 3.
Yay.
Just randomly worked out that way. Now, let's talk about question number 10 with the Earth-Moon problem.
I got something inside the Earth's
You
radius.
should. And that's a cool
Sorry,
deal.
probably not right.
Did get inside the Earth as well.
So, on a bigger scale, here's the sun, here's the moon, and here's our rock, okay? So the center mass, if you do that right, is actually lies within the Earth. That's what's actually moving when we go around the sun. That center of mass is what's going around like this. So what that means is that the moon and the Earth actually have a little bit of a wobble to it. So this is actually cool that the Earth and moon, that center of mass is inside the Earth, because if it had been like, say, halfway in between, our orbits would get really weird, because we would be moving around the sun, but yet those would be going around like this as it goes around the sun. Yes.
It's like
So
Like one of those spiral graph
it
things.
still happens,
Be wacky.
but because our center of mass is inside the Earth, it's not pronounced. But here's the cool thing about the Earth and the moon. So the moon is said to be tidally locked to the Earth. So what that means is that as the moon goes around the
So
Earth,
efficient.
the time that it takes for the sun to go around the Earth, for the moon to go around the Earth, is the same amount of time it takes for the moon to rotate once on its axis. So what that means is that as the moon goes around, like if you view this golf ball saying vice 1, if I'm the Earth, as the moon goes around like this, the only thing you see is vice 1. Okay? So the cool thing about the Apollo 8 missions, which was the first one to actually go around the moon, was that they saw the backside of the moon. So they were those guys, the first 3 human beings to ever see the backside of the moon. Like no one had ever seen that up until that point. So that's like, what did you do? I was the first one to see the backside of the moon. Now, it's not necessarily the dark side of the moon. This isn't like the Pink Floyd album. Mainly because of the fact that, if you look at this as like being the sun, okay, when you're here, like if this is the sun, this would be like a full moon. Yeah, you've got the dark side. Okay, so on a full moon, the side away from us is in the shadow. But when you have a new moon, that side's facing the sun. So the back side of the moon isn't always the dark side of the moon.
I guess that makes sense because like a solar eclipse, like
Yeah.
Yeah.
you'd have to.
Yeah. So don't confuse the dark side of the moon with the back side of the moon. On number 8, both of your answers on number 8, this is an ish, should be around 2, as should be your answer to number 7.
Is 1.6 around two?
Can I not read?
On number 8?
Yeah.
Yeah. Okay, are we good?
Yeah, I figured out my mistake.
What'd you do?
PEMDAS failed me. Miserably too.
What, on 8?
Don't you hate that?
No, 4. Number 4A.
Did you try and do your moment of inertia calculation all at once?
Yeah, I think so. I got like 0.03
For which answer?
for 4A. I don't know how I got.
I mean, that's close to your moment of inertia.
Can I
but
see your
it's
4C?
not your...
Oh my God, yeah, your answer to 4A should be 40.
Yeah, I got it now.
Thank God I gave you a hint. Okay, anything else going once, going twice, sold?
7.
What?
Multiple choice. That one was kind of weird.
That one was kind of weird.
Yeah.
I
Oh, yeah.
I
Oh,
concur.
and 1/2. That's the reason.
Okay. What did I say about the answer to number 4? What happens to the center of mass?
It
Gonna
changes.
stay in this
It
same
doesn't
spot.
change. I'm with you.
Same idea on number 7.
So it would be D.
Yes.
Right?
Okay.
He's literally given the answer to like every single one of these.
Not
Not
directly,
6.
but I
Let me see
certainly.
number 8,
We didn't talk about
please.
6.
8?
Not
8.
six, but like
He said it was around 2. I
five-
don't have
five-
around 2.
I literally
I
wrote
need
it
to
out.
know what you did.
2.4, 1.6.
I didn't count the squares for you. I just showed you how to do it.
Yeah, no, on number 5 of the momentum one.
Oh,
you literally wrote
to square
the
No, but see, but that problem's in terms of D, so I didn't technically write out.
And it's in terms of momentum of F and momentum of I, not final momentum of inertia.
So I
And
had
we didn't
10
talk about
20.
6 at all.
Are you complaining about this?
No, I'm just saying that you did give it. So if somebody gets it wrong, it's just completely on them.
I'll give you that.
Well, what if they like didn't do their assignment? Would that also be completely on them?
Ooh, that was a shot across the bow.
Not
The gap
me.
showing. That's a shot across the gap. Okay. Anything else? Going once, going twice, sold. Stop you on the camera.